Welcome to WikiPodcast. For as long as humans have looked up at the stars, watched an apple fall, or simply felt the warmth of the sun, we've been asking these fundamental questions.
Right. What's it all made of? Why do things move? How does it all work?
That deep, ancient quest for understanding. That's really the beginning of physics, isn't it?
It absolutely is. It starts with just plain wonder, then asking, better questions, more precise questions.
And building knowledge, step by fascinating step.
Exactly.
And today we're taking a deep dive into that incredible story. This is The History of Wonder, Physics Through the Ages. We've got this great stack of source material you shared, tracing this whole journey.
Yeah, from the very first philosophers right up to the frontiers of modern science.
So our mission here is to kind of cut through the noise, pull out the really crucial insights, the major turning points.
Ha-ha moments, yeah. Those times when our whole view of reality just shifted. We want to give you that shortcut to being well-informed on this epic history.
Because these steps, they didn't just change science books. They changed everything. Technology, philosophy.
Our whole place in the cosmos, really.
So let's dive in. Where do we start?
Let's go way, way back. Ancient times, physics wasn't really a separate thing then.
Right. It was all mixed in with philosophy, just trying to make sense of the world.
And in ancient Greece, you get figures like Thales starting to look for natural causes, not just saying, oh, the gods did it.
He thought everything was water, originally.
That was his idea, yeah. Others, like Anaximander, debated elements. Heraclitus was all about change and time. They were searching for order within nature.
And then comes Aristotle. Huge influence.
Oh, massive. For centuries, he tried to build a whole system based on observation.
Yeah.
The four elements: earth, water, air, fire.
And his idea of natural motion, like a stone falls because its nature is to be down with the earth.
Exactly. It felt intuitive, explained everyday stuff. His ideas really stuck.
But even then, others were pushing boundaries, using math and observation, weren't they?
Definitely. Think of Eratosthenes, measuring the Earth's circumference with shadows and geometry. Astonishingly accurate, too.
And Aristarchus, suggesting the Earth goes around the sun. That was pretty radical, then.
Hugely radical. Directly challenging Aristotle's Earth-centered view, way ahead of his time.
And Archimedes. You can't forget Archimedes.
No way. He was this bridge between theory and practice. Mechanics, hydrostatics, why things float. He showed math wasn't just abstract, it described the real world. Levers, buoyancy.
Proving math and nature were linked.
Absolutely. And it's important to remember this wasn't just Greece.
Right. Our sources mention India early ideas about atoms, like Canada.
Centuries before it really took root in Europe. And Aryabhata suggesting the Earth rotates. Nilakantha Sommayaggi had a kind of semi-heliocentric model, too. Really interesting stuff.
And in China.
Magnetism. The compass. Think how that changed the world. Shenkuo and the camera obscura, showing early insights into optics.
Okay, let's jump forward a bit. The Islamic Golden Age. Crucial period.
Absolutely crucial. Roughly 7th to 15th centuries. They weren't just preserving Greek knowledge.
Though they did that incredibly well, translating everything.
They did, but they built on it. They tested it. They corrected it. Think of Ibn al-Haytham.
Optics, right?
Yes, basically founded modern optics through experiments. He showed light travels to the eye, not from it. A fundamental shift based on actual tests.
And what about motion? I remember reading about Ibn Sina, Avicenna.
Yes. His idea of impetus, that a thrown object keeps going because the thrower imparts some kind of persistent quality to it.
Which sounds a lot like inertia, or anticipates it anyway.
Yeah.
Better than Aristotle's must be constantly pushed idea.
Much better. And others like Abu Barkat al-Baghdadi talked about acceleration, Ibn Bajjah about reaction forces.
And this knowledge flowed, influencing later thinkers, like Al-Tusi's work potentially influencing Copernicus.
There are definite links and lines of transmission, yes. It shows how connected this history is.
So eventually these ideas filter back into medieval Europe.
Right, often through those Arabic translations. And you get the scholastics grappling with Aristotle, trying to fit him with theology.
But it wasn't just passive acceptance, was it? There was critique, new thinking emerging.
No, definitely not just acceptance. You see this growing urge to quantify, to measure. And figures like John Philoponus, much earlier, and later Jane Buridan, refining that impetus concept, they were starting to question Aristotle based on what they observed.
Planting the seeds for a big change.
Exactly. It wasn't a dark age intellectually. It was digestion, refinement, setting the stage.
Which brings us right to the scientific revolution, 16th, 17th centuries. A feeling that the old explanations weren't enough.
A real shift towards math, towards experiment. Let the results guide you.
And here come the big names. Copernicus.
The game changer. Putting the sun at the center, not just rearranging the planets, but fundamentally shifting humanity's place in the universe after 1,400 years.
A mathematical argument, primarily.
Yes, but a powerful one. Then Kepler takes that, uses Tycho Brahe's super accurate data,
And figures out the planets move in ellipses, not perfect circles, with mathematical laws describing how they move.
he started treating astronomy as actual physics of the heavens.
Then Galileo, maybe the key figure for bringing in experiment.
I'd argue yes. He didn't just trust Aristotle on motion, he tested it, dropping things.
Right, showing that weight doesn't determine falling speed, ignoring air resistance.
And his telescope. Seeing Jupiter's moons, Venus's phases, direct evidence against the old model, he insisted nature's language was math.
Which got him into a bit of trouble.
Yeah. Quite a bit. Meanwhile, you've got Descartes.
The grand mechanistic philosophy, everything is particles bumping into each other.
Basically, yeah. A clockwork universe governed by universal laws. Huge emphasis on math. Plus, he gave us analytical geometry, a vital tool.
And Huygens, another key player.
Brilliant physicist. The pendulum clock, huge for accurate experiments. Wave theory of light, formulas for forces. Really brought mathematical rigor. Some call him the first theoretical physicist.
Okay, and this all leads up to Newton.
Sir Isaac Newton. The synthesizer. The unifier.
It's hard to overstate his impact. Laws of motion.
That explained everything from apples to cannonballs, and then universal gravitation.
The same force holding us down keeps the moon up there, unifying Earth and heavens.
One elegant system. And he invented calculus to do it, all laid out in the Principia.
It's interesting he focused on describing gravity mathematically, predicting its effects, even if he couldn't explain the why of it, unlike the Cartesians who wanted a mechanism.
He famously said, hypotheses non fingo. I frame no hypotheses about its ultimate cause. The math worked, predicted things accurately. That was the key for him. Plus his work on optics, color, the reflecting telescope.
His framework just dominated physics for the next 200 years, changed everything.
Absolutely. And alongside Newton, you had Gilbert studying magnetism, Boyle with his gas law,
Scientific societies popping up, sharing knowledge.
and the first hints of thermodynamics driven by practical needs, like the steam engine.
Guericke's vacuum pump experiments showing nature doesn't abhor a vacuum, contrary to Aristotle. Early engines from Papin, Savory, Newcomen.
Yeah, the Industrial Revolution was starting, and they needed to understand heat, energy, work, setting the stage for the next big phase.
Right, moving into the 18th and 19th centuries, classical physics really matures and expands.
Yeah, the 18th century sees Newtonian mechanics refined with powerful calculus rational mechanics. Euler, Lagrange, the Bernoullis, applying it to everything.
Astronomy keeps marching on. Halley's Comet prediction comes true. Uranus is discovered.
Cavendish even measures G, the gravitational constant, basically weighing the Earth.
And that curiosity about heat and electricity continued, thinking of them as imponderable fluids.
Which drove experiments, new instruments like calorimeters, Leyden jars for storing charge, leads to discoveries like latent heat by Black, Franklin figuring out positive and negative charge.
Okay, but the 19th century, things really accelerate there, right? Especially with electricity and magnetism.
Oh, massively. First, you get analytical mechanics refined further by Hamilton, and clearer statements of energy conservation from Mayer, Joule, Helmholtz. Energy is key.
But electromagnetism, that's the big story. Volta's battery gives steady current.
Thomas Young shows light behaves like a wave, challenging Newton's particle view for a while.
Then Ørsted sees a current move a compass needle, linking electricity and magnetism.
Boom. Then Ampere works out the forces. Faraday and Henry discover electromagnetic induction, the basis for generators, motors, modern life, basically. Ohm gives us his law for resistance.
It feels like all the pieces are coming together.
And then Maxwell puts them together, James Clerk Maxwell. His equations, it's just beautiful. They described all known electric and magnetic phenomena.
And predicted something totally new.
Electromagnetic waves traveling at the speed of light.
Which suggested light was an electromagnetic wave.
Exactly. And when Hertz actually detected radio waves experimentally, confirmation, a stunning unification. Optics, electricity, magnetism, all one thing.
Incredible. What else was big in the 19th century? Thermodynamics.
Yes, it became a proper science. Joule quantified the mechanical equivalent of heat. The first law, energy conservation, gets formalized.
And the second law, Entropy.
Right, Clausius, Kelvin. Realizing heat only flows one way naturally from hot to cold, entropy is a measure of disorder or energy unavailable for work. It gives time a direction, in a sense.
And a whole new way of thinking emerges, too, statistical mechanics,
Yeah, Boltzmann Gibbs, instead of tracking every particle, use statistics to understand the average behavior of huge numbers of them.
which gives a new meaning to temperature, pressure, and entropy as molecular disorder.
A brilliant bridge between the microscopic and macroscopic worlds.
So, end of the 19th century, physics looks pretty complete.
Sure.
Classical mechanics, E&M, thermodynamics, they explained almost everything known.
It felt like just tying up loose ends. Lord Kelvin famously mentioned just a couple of small clouds on the horizon.
Those clouds turned out to be hurricanes, though.
They absolutely did, because some experiments just didn't fit. Blackbody radiation, how hot objects glow, the photoelectric effect light knocking electrons off metal, the Michelson-Morley experiment failing to find the ether light was supposed to travel through,
These were the cracks that broke classical physics open.
leading to the two pillars of modern physics, relativity and quantum mechanics. And it started with probing the atom.
X-rays, radioactivity showing atoms weren't immutable. Thomson discovering the electron.
The first subatomic particle. Then Rutherford's gold foil experiment finding the tiny, dense nucleus. The atom was mostly empty space, not a plum pudding.
And then Einstein, 1905, his miracle year.
Special relativity. Space and time aren't absolute. They're relative, intertwined. The speed of light is constant for everyone.
Leading to weird effects like time slowing down for fast travelers.
Time dilation, length contraction, and ipsa sperno, mass is energy. A profound insight. Made the whole idea of the ether unnecessary.
And that wasn't all he did.
Not by a long shot. 1916, general relativity. Gravity isn't a force, it's the curvature of space-time caused by mass and energy.
So planets orbit the sun because they're following curves in space-time, not because they're being pulled.
Exactly. It predicted light bending near stars, black holes, became the foundation for modern cosmology. Completely replaced Newton's view of gravity for strong fields and large scales.
Okay, that's one pillar. What about the other? Quantum mechanics.
Started with Max Planck trying to solve that blackbody radiation problem in 1900. His desperate idea, energy comes in discrete packets, quanta.
Not continuous, but chunky.
Right. Einstein then used that quantum idea in 1905 to explain the photoelectric effect light itself acts like particles, photons in that interaction.
Then Niels Bohr applied it to the atom in 1913.
Explain why atoms are stable, why they emit specific colors of light, electrons in specific orbits or energy levels. A huge step, though still a bit of a hybrid model.
The full theory came later.
Yeah, the 1920s. Heisenberg, born Jordan with matrix mechanics. Schrödinger with his wave equation. Dirac unifying things. Pauli, it was an explosion.
And it was
Weird.
probabilistic.
Fundamentally probabilistic. Heisenberg's uncertainty principle. You can't know everything perfectly, like position and momentum at the same time. Challenged causality.
God does not play dice.
Einstein's famous objection. But quantum mechanics works. It's the bedrock for understanding atoms, molecules, semiconductors, everything small.
So this creates the split. Classical physics for the big stuff, modern physics, relativity, and quantum for the very fast, very small, very massive.
Pretty much. And the story continues, trying to build on those modern foundations.
Post-World War II, the big push was making quantum mechanics work with special relativity.
Quantum field theory. QED, quantum electrodynamics, developed by Feynman, Schwinger, Tomonaga. Incredibly precise theory for light and matter interactions.
Which led into particle physics,
Yeah.
trying to understand the forces and particles inside the nucleus.
Exactly. Yukawa suggested forces are carried by exchange particles. Then particle accelerators started finding a whole zoo of new particles.
Needed a way to organize them.
Delman's eightfold way, the quark model, chromodynamics for the strong force, leading eventually to the standard model.
Standard model. That's
Okay.
the current big picture for particle physics.
It is. It uses gauge theory to unify the electromagnetic weak and strong nuclear forces. Describes all the known fundamental particles and how they interact. Hugely successful, experimentally verified. But it doesn't include gravity. That's the big missing piece. And it doesn't explain everything we see in the universe.
Like dark matter and dark energy.
Precisely. Cosmology, powered by general relativity, showed the universe is expanding. Hubble, Slipher, led to the Big Bang Theory. Lemaitre, Gamow, got huge support from the cosmic microwave background discovery by Penzias and Wilson.
The echo of the Big Bang.
Right. But when we measure how galaxies rotate, how the universe's expansion is accelerating, The visible matter isn't enough. We need dark matter for gravity, dark energy for acceleration. We don't know what they are.
Huge mysteries. And what about the Higgs boson? That was a big deal recently.
Huge deal. The Higgs field was theorized decades ago by Peter Higgs and others as the mechanism that gives fundamental particles mass. Finding the Higgs boson at CERN in 2012 was the confirmation, the last missing piece of the Standard Model itself.
But understanding the Higgs might lead beyond the Standard Model.
Possibly. It could be linked to inflation in the early universe, maybe even dark energy. It's a very active area of research.
And physics itself keeps spreading out, right? Its tools are used everywhere.
Absolutely. Geophysics, astrophysics, biophysics, material science. It's incredibly interdisciplinary now, and the scale often requires huge international collaborations.
So looking back at this whole sweep, from ancient wonder to quantum fields and dark energy, it's quite a journey.
It really is, driven by that fundamental human need to understand, questioning assumptions, developing new tools, math, experiments building on what came before.
And yet, the biggest questions might still be out there. Unifying gravity, understanding dark matter and dark energy. The nature of reality itself.
The quest definitely continues. What does this ongoing search, building on centuries of discovery, mean for our future understanding? It's exciting to think about.
Thanks for listening. Write us your opinion in the comments on what historical physics discovery you found most surprising. Subscribe to the channel to help more listeners reach our episodes. Thank you and have an amazing day.